Good evening, good morning, and good afternoon for those of you in different parts of the world. We thank you once again for joining our
Buenos días, buenas tardes.
Kiskit Fall Fest.
Gracias por
And
unirse.
um, Danielle, you do not need to interpret right
Ok,
now.
ok.
I am going to actually, no, you're correct. Let me do this again. Every time I think we have this right. We'll get it by the time we're done, I promise. Uh, Let me see. Interpretation. So Daniel is going to be doing Spanish. Voy. Daniel Ruiz video or Daniel, sí, Daniel Ruiz video, ¿verdad? De inglés al español. Okay, y después, after again, you guys switch over and then Nancy will do the interpretation. Okay. All right. So good evening, good morning, good afternoon. We are a little bit over halfway through our incredible event. We thank you for your time, your presence, your attention, and we are incredibly excited to bring you closer to quantum machine learning today through both Sadikin's completion of his long series to help you pass the course and through one of our experts that we're going to be presenting shortly. Just as a high level of our agenda, we are going to go through quantum risk management framework, and then we're going to shift back into our quantum chemistry track. So quantum machine learning, quantum chemistry, and then we're going to wrap up with the last module of our quantum machine learning. Next week, we're going to focus on our quantum security cryptography. And today I will be releasing one of the hackathons so you can get started on that. Remember, please, that our certification quiz is going to be available on the Discord channel along with the other notebooks. You do not have to complete those notebooks and send them back to us. We want you to be able to explore your understanding deeply with the completion of the code. So we will also be giving you the solutions after the quiz. Once again, let me introduce you here to oh, interesting. Okay, why is this not working? Allie, it really wants you to present today. I'm kidding. So, without further ado, I'd like to introduce you to Gian Yala. He is the founder and CTO of IQ Leap Research and CTO of Data Tech AI, the lead advisor for the Quantum Incubation Center at RGUKT, International Institute of Informational Technology. Srikakulam, and a quantum machine learning researcher working on the intersection of artificial intelligence and quantum technologies. With a career spanning defense, research, academia, and industry, he brings a unique perspective to building the next generation of intelligent systems. Currently, his research is focused on quantum machine learning and quantum AI, exploring how quantum principles can accelerate machine learning models. An active speaker and trainer, he is passionate about making cutting edge technologies like generative AI, agentic AI, and quantum AI accessible and impactful. We are very honored to have you here, Dr. Gyanyala, and hear about your quantum risk framework as it aligns to integrating amplitude estimation, entanglement analytics, and variational optimization. So without further ado, if Daniel, you could start interpreting in Spanish, and then I will allow your share, please. To our attendees, please make sure that the chat is enabled. You know that you can ask on Discord or in the Zoom chat.
Okay. So, can I start?
Yes, please take us away, and thank you.
Yeah, sure, sure, sure. So, first of all, the same good morning, good afternoon, good evening to everyone. And thank you for the introduction, Nidia. Okay, so I am Dr. Alla, and first thing I want to say is I have very limited time in order to explain the big framework out here. So I will just try to make sure that I provide the high level interpretation of what exactly are we supposed to do in quantum risk management framework. And I will try to provide you with insights in such a way that you guys will be able to understand what exactly is this quantum risk management framework in finance and how exactly it's going to make an impact and how exactly it is advantageous on comparison to your classical machine learning or classical risk management frameworks and stuff like that. So, yes, first of all, before actually going into and before actually directly starting with quantum computing and all the stuff, I would like to first explain about what exactly do you mean by this risk management framework when you're dealing with this quantum computing. Now, before directly going into quantum, let's directly start with what exactly is this risk management framework. Very simple, very straightforward, and very easy. So, what exactly is this risk management framework is that now when you're dealing with finance related operations, like let us consider you have a huge portfolio. Because in finance, we guys will be having a portfolio, a huge portfolio, where we'll be having our own assets and the stock which we need to buy and all the things. Okay. So, and then we need to ensure that whatever stock we are buying or whatever assets we are playing with give us profit. That's our main motto, right? We will not invest in portfolio so as to get loss. We will invest in portfolio to get profits only. That's a basic deal about it. So that's why we will make sure and we should be very important and we will always have a view or have an eye on what exactly is happening in this entire portfolio. Okay. So in when you're dealing with this particular operation of managing this entire portfolio, there comes some terms called as risk management, fraud detection, portfolio optimization, and a lot of. Okay. So what exactly is everything? And then I will come to what exactly did we do. First thing, fraud detection. When we are actually planning on a particular portfolio and if I actually want to invest something, then I should make sure that the history of that particular asset is not consisting of or is not comprised of any sort of fraudulent data or any type of fraudulent transactions. Why? Because obviously, let us consider you're gonna buy a product. And if that product reviews are half of them are fraud reviews, will you be able to buy that product? Obviously we will not buy the product because half of them are of fraud reviews, right? So the same logic comes in my portfolios as well. So if I see some stocks like stock A, stock B, stock C, or ticker A, ticker B, ticker C. Now, if ticker A is showing 97% of returns, I will not directly blinded by that 97%. I will make sure that that 97% is legitimate. So I will make sure that I will search for any type of fraudulent transactions in that stock A, and if there's no fraudulent transactions, then only I will be able to trust that stock A and then I will invest in that particular stuff. So that's one of the deal. So that's one of the thing which we always follow when we are dealing with the risk management. I mean fraud like this finance management. Second thing is portfolio optimization. So what exactly do you mean by this portfolio optimization? Same thing. Let us consider I have stock A, stock B, and stock C, which I want to invest in. Okay, and I have something like $100,000. Now I need to make sure that I need to invest this X amount of X amount of bucks which I am having into stock A and Y into stock B and Z into stock C, right? Because I totally want to invest $100,000, but I don't know the efficient way in which I can invest those $100,000 in my stock A, in my stock B, and in my stock C, so that I will get huge returns with minimal loss. Because at the end of the day, I need to get huge returns with a minimal loss. Okay. So for that reason, we will perform something known as a portfolio optimization test. So in that portfolio optimization, what we'll be doing is that we will take into account the entire workflow of that particular stock. Let us consider stock A is Apple, Apple ticker. Now I will make sure that I will see an entire history of that Apple ticker's movement. Like the entire past 10 years or past 15 years of the prices of this Apple ticker. And then I will take that into account and then I will optimize it accordingly. And then I will tell like, okay, bro, you're having three stocks now. Let us consider Apple, Microsoft, and Tesla. So in these three stocks, Apple stock is showing heavier returns. So you invest 60% of your amount there. And in Microsoft is showing something like 30% of return. So you invest 30% of that your amount there. And Tesla, you invest the remaining 10% what you have. So in this way, my optimizer will tell me how much to, what can I say, how much to invest into my portfolio, how much amount I should invest in my portfolio. That will be given by my, what can I say this as, portfolio optimizer. That's the main task of this portfolio optimizer. The efficient amount which I should be investing in a particular stock so that I can get huge returns. That is my portfolio optimization. Now comes the third deal. The third deal is a very important one, which is known as the risk management. Okay, so what exactly do you mean by this risk management? So in the screen, you can see these terms which are included, called as, okay, yeah, called as value at risk and conditional value at risk. So in the traditional approaches, you can see that. So what exactly do you mean by this value at risk and conditional value at risk? So if you're not into finance, definitely you're gonna get confused by this one. So let me tell this in a very simple manner. You don't need to know about this in that detailed way. So simply to put, value at risk simply tells you the minimum amount or the threshold loss amount which you can have at a particular confidence interval. That's it. Simply to put, that's not a real definition, but simply to put, you can understand in this. So the threshold amount in which I can get a certain percentage of loss. That's it. Okay, simply to put, you can understand in that. And conditional VAR is like an extension of this VAR. So just because my value at risk is perfect, I can't completely depend on it, right? So for that, I'll be having a conditional value at risk, like a conditional statement. Okay, okay, somewhat extensive. Like if my value at risk is something like 90%, my conditional value at risk will be something like 92% or 93% approximately. So that's the entire the extension of this value at risk. Value at risk gives me a certain value. Okay, completely alright. Conditional value at risk will give me an extension of that. Okay, bro. So at value at risk, I got to know that this is the deal. But if in worst case, if something happens, then what should I be doing? So that worst case error is given by my CVAL. Okay, you can just simply consider it like this. So in mathematics or in physics, we used to have this plus or minus thing, uncertainty, right? So when we actually measure, we will not directly measure like 5 centimeter or 10 centimeter. We will be measuring 10 centimeter plus or minus 0.3 or 5 centimeter plus or minus 0.2. So that 5 centimeter thing is there now. So that is given by my value at risk. That plus or minus 0.2 plus or minus 0.5 is there. That is given by my conditional value. Got it? So simply to put, you can consider like this. Now, what exactly do these terms help us? How or what exact and how exactly do these terms help us? Then, very simply to put, with the help of these values, I can see where I am having huge risk and I will try to get rid of that risk. Okay. So I will make sure that these values will tell me where I am having huge risk in my portfolio. Okay. So where do I have huge risk in my portfolio? So I'll be getting that logic. And when these guys will give me those values, I'll be knowing like, okay, so at this point I have huge risk. And when I know at this point I have huge risk, what I will do, obviously, I will get rid of them because I want returns. I'm not an adventurer, right? I want returns. I don't want any type of, risk to take care of. Okay. So that's a simple deal here. So for that reason, we should be having this risk analysis model. So these are the three main things which we often see when we are talking about the finance domain. So in finance domain, the first main thing is our fraud detection. And the second main thing is our portfolio optimization. And the third main thing is our risk analysis or risk assessment. Because for every portfolio, we need to make sure that it is not having any fraudulent data. We need to make sure that we optimize that portfolio so as to get huge returns. And we also need to make sure that we need to remove all the sorts of risks in my portfolio. Why? Because I want it to be perfectly fine and I want it to give me huge returns. Okay. Now, technically, if you take any big companies like JP Morgan Chase or like HSBC or any type of big companies who are dealing with this particular stuff, they will use the classical methods. So I'll just name you some of them. I'll just name you one of them. It's more than enough. So when we are dealing with the portfolio optimization, we have something called as Markowitz portfolio optimization. So that's a classical phenomenon. So it works very well that literally every company which you can think of for this portfolio optimization uses that Markowitz portfolio thing. So similarly for fraud detection, the best model in machine learning is the random forest one. But when it comes to deep learning, we have a huge neural network architecture. We can classify my data set very clear. So everything is cool. Okay, similarly in risk assessment also, I have a lot of stuff. So in risk assessment, I will be using something called as a Monte Carlo tree. Okay, so that Monte Carlo tree is mostly used when we are dealing with the game theories or when we're dealing with the game Wala stuff. Okay, now why exactly do I need quantum here? Because my classical is doing good, bro. JP Morgan and Chase is a very good company, and that company is using my classical thing. Why will I need quantum? What is the advantage of this one? So for that, I have this beautiful slide in front of you guys, which tells me what exactly and why exactly do I need quantum at this point. Simply to put, when you are dealing with the traditional approaches here, what exactly we're talking about traditional approaches means that approaches which are used by the organizations. When we are dealing with the traditional approaches, we can see that they include the stuff which I told you, value at risk and conditional value at risk, and how they will they or how are they found? They are found by using something known as a classical Monte Carlo trees. That's what I mentioned, right? So it completely resides on classical Monte Carlo trees. Okay, is Monte Carlo or is MC3? I'll just call it MC3. Is MC3 very bad one? No, it's not a bad one. Like every game what you play, every deciding game what you play resides on Monte Carlo. So that won't be a problem there. So it's very perfect. Then why exactly do I require quantum? For n assets or n rows of data for in your portfolio. In your portfolio, you'll be having n rows of data. Let's just consider n rows of data. So for those n rows of data, my MC3 will take n iterations or O of n iterations in order to take the good values out and in order to do my var and cvar. Okay, for n rows, I'll be having n iterations. Okay, so I have 10 rows, 10 iterations, completely fine, right? Why should I need all these things? Very simple. If you want your model to be perfect, we will be requiring huge data. So let us consider you want to be so smart. If you want to be so smart, will you study only one book or will you study 10 books? Obviously, we'll be studying 10 books because the more I read, the more smart I will get. Approximately, we can consider in that way at this point. So, if I want my model to run perfectly fine, I need to have more data. So, the companies, they will have data in the form of 500,000 rows or 600,000 rows or 800,000 rows. So, they will be having the rows in this way. And if I'm having that many rows, the number of iterations will also be that much. So based on the number of rows, the number of iterations increases. Okay, the number of iterations is one point. The other point is complexity in the data. Each row will have a lot of columns so that the understanding, so the ability to understand those all values will become more complex. And let us consider one row has 15 columns, meaning I should understand the relation between these 15 values, and I need to do that for 800,000 rows. So 800,000 into 15 approximately. So I need to do that much stuff and that much calculation in my mind to give you a proper output, right? So for that reason, your Monte Carlo trees or your MC trees will stop at certain point or will break at certain point. Why? Because as I already mentioned, n iterations, right? N iterations for 15 columns gone. Because then tree length will become so huge that it will be very much inefficient in terms of memory, in terms of resources, as well as in terms of mathematical calculations to do. So these tree values will be too much and it will be very much inefficient for my classical Monte Carlo tree to handle this such data. Why? Because as the number of rows increases, the depth of the tree will increase. So the depth of the tree. So Monte Carlo is like a tree. So I hope you guys are very well aware of binary trees and DAG graphs and trees, right? Like trees. They will look like a flow diagram from top to bottom, from root to leaf, trees. So as the number of iterations increases, the depth of the tree, meaning the length of the tree will keep on increasing, as well as the data will also be complex in nature so that I cannot actually catch the particular data. And that's where I will be seeing a lot of inefficiency. Now, for that reason, we will be having the quantum computing stuff for doing this risk management thinking. As I already mentioned, in finance, we have four main things, right? Fraud detection, optimization, risk management. Okay? Sorry, three main things. Now, all those three main things, we will just mix it in and we created this quantum risk management framework. So in this quantum risk management framework, meaning the entire thing, it covers the entire risk modeling framework of what we exactly need in finance. So in this quantum risk management framework, our main aim is to simply increase the efficiency of this risk management thing. So that's our first main goal. I don't want my trade depth to be increased and I don't want to give any type of inefficient answers to my customers or inefficient answers to anyone here. So I need my answers to be way more perfect and way more simpler. And I need my answer to be given in a very simple way, right? So for that thing, I will be taking the help of this quantum computing frameworks. What exactly are we doing in this quantum computing framework? Very simple. So we brought in three main categories here. So the first thing is quantum amplitude estimation. So why do I require this quantum amplitude estimation? When I talked about two main values which I actually require to do the risk assessment and to take out the values which are at huge risk, I mentioned two main terms or two main definitions. So those two main definitions are value at risk and conditional value at risk. So these are the two main things which I mentioned when I said that I will be identifying the places where I have huge risk, right? Now, how can I exactly identify this? What is the type of problem? So let us consider I have huge data, or let us consider I have a very good picture, and I want to spot out two, or let us consider I have a bag, and that bag has a piece of blocks or something. And your task is to find red color block. Okay. Now, in that case, what is the type of operation we are doing? We are doing something called as a search operation. Yes or no? So I have a bag, and in that bag, I have many blocks. And in that many blocks, my task is to take the red block out. So it is a simple search operation, right? Similarly, when you're talking about portfolio and when I'm talking about value at risk, bro, conditional value at risk, I will take out the risky element. I'm simply saying, right, bro, out of all the things which I'm seeing in my portfolio, I need to take out the guy who is having huge risk. Meaning, simply I need to search the position which has huge risk, right? So, this particular trade where I want to find the value at risk and conditional value at risk. So, this operation comes under a basic search operation. So the words which I'm using are very big, like value at risk, you need to find, you need to do risk analysis and all. But simply to put, it's a basic search operation which we are trying to do in my portfolio. I will try to do something called as a search operation into my portfolio. and I will try to identify the points or the places or the particular stocks where I'm having huge risk, and I will take them off or I will kick them off. So that is my main deal. And for that main deal, I have something called as quantum amplitude estimation. So in this through this quantum amplitude estimation, I can clearly find the target value in an easier manner compared to Monte Carlo search trees. So that's my first main thing. And second main thing what I'm trying to use here is quantum approximate optimization algorithm. Okay, which is known as QAOA. Here I get QAOO, but it's technically QAOA, quantum approximate optimization algorithm. Okay, so what is this QAOA algorithm? So it is simply nothing but an optimization algorithm in quantum. So it is known as a totalized annealing algorithm, where it goes in a very simple way. Very simple way. The simple way is this. Just try to understand this in this manner. The deal goes like this. What is the optimum value? Very simple. Let us consider you're walking in a plane, okay, or a plateau. So if you are going in or if you are going in a plateau, if you're walking on a plateau which consists of mountains and which consists of terrains and which consists of slopes and all those things, okay, and which consists of holes as well. Now if or let us consider ball rolling, so we have that game. I think the game name is itself is a rolling ball game. So where the ball will roll in on the mountains, under the mountains, or inside the pit and everything. Okay, so optimization is the same task where the ball is there, right? So that ball will be my answer, or the ball will be the indicator, and the optimum position is there. Now, so where will I get the optimum value? When the ball reaches the lowest point in my land or in my plateau. So I have a plateau. I'll be having something called as an energy landscape. It's a landscape. Okay. So in that landscape, the lowest point is my optimum point. So that's how optimization exactly works. So my entire problem will be represented in the form of an energy landscape, and the lowest point of that energy landscape provides me the optimum answer. Now, my quantum approximate optimization algorithm, I'm not going into the details, but simply to put, it will encode the entire problem into something called as a Hamiltonian problem, and it will slowly try to change the energy value. It will slowly try to change the energy values so that the state will evolve from a basic state to the solution state. So what will happen in this evolution from basic state to solution state is that the movement of ball is there, na? The ball will slowly move and it will end up in a very deepest point in my energy landscape. So the movement from this initial position to that solution state. So it is simply analogous to the ball slowly moving in my plane and reaching to the bottom point of my energy landscape, thereby giving me the optimum solution. So that's my quantum approximate optimization algorithm, where I exactly will find the optimum solution for my problem by keeping my ball in the deepest point of my energy landscape. And third thing is VQE. Why do I require VQE here? Very simple. I need to find the optimum solution at the end. I found the optimum solution. After finding the optimum solution, I should use it properly. So for that, I'll use VQE. Simply to put, there's nothing here. Now, our risk management framework, as I already mentioned, I mentioned the theory part before. Now coming to the actual application, my risk management framework consists of three main deals. Quantum risk amplitude estimation, which I already mentioned, search task, simple search task. For that search task, I'll be using the amplitude estimation, and systemic risk analysis for contagion monitoring. What is this contagion monitoring? I'll be explaining that. And third thing is VQRO. That is my quantum optimization, variational quantum risk optimization. Okay, so risk optimization. That's what I told. Now portfolio optimization, bro. Okay, that is my third day. So the three days I explained are here. Now, what exactly is happening here? So what is an advantage? Very simple. When I'm dealing with MC trees, we had an iteration of O of n, again classical things. But when we are having here that when we are using these three values, that is risk amplitude estimation, systemic risk analysis, and variational quantum risk optimizer, we got the sample complexity of only O of root n. Bro, what will this root make a difference, bro? 4 under 2 or 9 means 3. That's it only now. How much it will make a difference? Very simple. Try to find a root for 800,000, then you will understand a lot. So for small values, there is no change. For small values, we will think like it's a minimal advantage only. But as I already mentioned in the beginning itself, the companies have the data of 800,000 rows, 500,000 rows or something like that. Try to keep a root for the 500,000 or 800,000. Then we will understand the real advantage of what our quantum is providing in here. Okay. Now, the quantum risk and estimation, the QRAE thingy which we use to search the where and see where and all the deals is giving us an advantage of root of n compared to n of our classical computing and a speed up of 150 speed up more than 150. Okay, so let us consider 150 times of speed. So for every 150 seconds that can be done in 1 second in my quantum. Why? Very simple. Risk amplitude estimation. Instead of using that MC trees, where I mentioned about MC trees, the depth will become more and the complexity, that is the connections of the nodes will become way more complex. And when all these complexity adds, what happens is that the efficiency will be less. Okay, as efficiency is less, the time obviously it will be more, right? So in classical stuff, we have a huge time to process. But in quantum, it is 150 times faster compared to the classical mechanisms. So this is an advantage which we see when we are dealing with this particular mechanism. Now, yes. So, what will we exactly do when we are dealing with QRAE? Very simple, very straightforward, and very easy. I'm not getting into mathematics and stuff to bore you guys, but let me tell this in a very simple manner so that you can easily understand it. Now, I will be using two things here. One is classical binary search operation, and second thing is risk amplitude estimation. So why will I use binary search optimization, binary search thingy in my particular this process? Very simple. I want to identify where my X threshold values. So I want to identify where my threshold values. That is, I told you when I'm explaining the where, right? The threshold value of X, which has a minimum percentage of loss, right? Approximately. So that threshold value of X is there now. So in order to find a threshold value of X, I'll be using my classical binary search operation. And with that binary search optimization, I will go through my entire portfolio of values and I will find my, what can I say, X value. The X value is the threshold loss value. Threshold loss. They are not my actual risk elements. They are not the risk elements. The risk elements will be inside my portfolio. So X is my threshold loss value. To find the threshold loss value, I'll be using my classical binary search. And after using classical binary search, I find my threshold X value. Let us consider threshold of X value is something like $253. Okay. Now I will be using the amplitude estimation process or algorithm or rules. So in QRAE, what happens is that very simply to put, I will observe all the points at the same time thanks to the superposition principle. And simply to put, what will I be doing is, if I observe any point which is different compared to others or which is breaking a particular threshold, then I will simply mark them. Okay? I will simply mark them off. What do I mean by mark them? I will simply give them additional signals, thereby making their amplitude huge compared to all the amplitudes. Very simple. Let us consider you want to provide or you want to identify the brightest kid in the classroom. So I will be checking each and every student's marks. And if I observe a student who's having good mark, I will give him a gold star. and he should pin the gold star on his shirt or on his uniform. So like that, every teacher will come and they will observe the marks in their particular subjects and they will pin the gold stars. Okay. Now when a new teacher comes who want to see who is the brightest kid, now he don't need to check the marks again, right? He can simply see the number of gold stars in the student's uniform. And the person who is having huge number of gold stars is the brightest kid in the classroom. Okay, so this is the basic concept of marking our target element, right? The same thing will happen in risk amplitude estimation. So it will simply check all the data points simultaneously at the same time thanks to the superposition principle. And if it observes any data point which has or which satisfied a certain threshold, it will mark that data. How it will mark that data point? Very simple. It will give it an additional amplitude. Okay, so let us consider all the amplitudes will be given in equal way. So let us consider there are 50 elements. So when there are 50 elements, every element's amplitude is 20, 20, 20, 20 ohm. Sorry, 2, 2, 2, 2 ohm. So every amplitude's probability or every data point's amplitude is 2%, 2%, 2%. The moment when I observe certain data point which has or which crosses a certain threshold, I will make it 4%. And I will make the other guy who is not even near 0%. Okay. So in that way, I will increase the amplitude or I will increase the probability of my target state. Or I can say my the state which is satisfying my particular threshold. So in that way, I can find a point where actual risk exists. Simply to put, at each iteration, I am pointing that guy, I am marking that guy. So when I'm easily trying to measure it, what happens? The value which is having huge amplitude will be given as the output, right? So in that way, I will be doing my QRAE, which is completely opposite to MC3s. So in MC3s, we'll be checking each and every node, going down, checking back, coming back, and all the deals. But in here, nothing happens. I will simply check if it is satisfying, add my amplitude or increase the amplitude. If it is not satisfying, leave it and go to next guy. That's it. And at the end of the game, I simply see the entire data points and the state which is having huge amplitude is my risk guy or is the guy which is having the huge risk compared to all of this. So that's a simple way of understanding amplitude estimation. Second thing is the risk scoring thing or systemic risk analysis. How will I do the systemic risk analysis? Oh, sorry. Yeah. So how will I do the systemic risk analysis? Very simple again. Now, a portfolio fails because of one main reason actually. So what is that main reason why my portfolio fails is that MCT's Monte Carlo tree. Yeah, correct. Okay, sorry. Now, so what exactly happens in a portfolio? Really, what exactly happens in a portfolio is that when one risk element is found, that risk element spoils your entire portfolio. So simply to put, I have three stocks, stock A, stock B, and stock C. And if I found a particular risk at stock A, then that stock A's risk will affect my stock B's data as well as my stock C's data as well. Because I'm talking about my overall portfolio. I'm not talking about the returns based on a single stock. I'm talking about the returns of my portfolio, my entire portfolio's returns. So if there's a one guy which is giving me risk, then that thing will eventually affect my second stock as well as my third stock as well. Same like they will say, now don't be with bad people or bad company, it will affect you. Same logic. If there's a one guy who is one stock which is having a huge risk, it will spoil the other stocks as well. Now, how exactly spoils the other stocks as well? Because there is something called as a connection points. So as you can see in the diagram here, so there are connection points. Okay. Similarly, when you try to model that particular portfolio mathematically, or when you try to visualize that particular portfolio, it will be like this chained structure or like a network structure. And if one guy, let us consider this circle is spoiled, then obviously all the circles or all the spheres which are connected to this particular sphere will also be spoiled, right? Same logic happens in my finance portfolio as well. If one token or if one ticker is spoiled or it consists of risk, the remaining all the guys which are related to that will also be spoiled. So in order to identify the risk spread and to minimize that risk spread, okay, I identify the risk in the first place. Second thing, I need to minimize the spread of this risk. So how can I minimize the spread of this risk? By using this systemic risk analysis framework. In this thing, we have something called as entanglement based encoding, where we will encode all the financial relations or finance network relations into my quantum state, and then I will entangle them. Simply to put, what is an entanglement? Deep correlation between two qubits is entanglement. Simply to put, that is a basic definition I can ever get for an entanglement. Deep correlation or heavy correlation between two quantum states is known as my entanglement. So similarly, what I'll be doing, financial network relations are there. So these network relations of my portfolio, I will encode them into an entangled qubit state. I will entangle the relations. After entangle the relations, I will perform something called as a purity measurement. Simply mathematically to put, purity measurement is a trace of the square of the density matrix, and there's a huge of things. So we should do something known as swap operations, and that this a lot of things will come into play, which I don't want to discuss about. So I will tell it in a simple way. What do you mean by purity measurements? The state of a quantum state which has low noise is considered to be the pure state. Simply to put, a quantum state which do not have any sort of noise, or which will not be disturbed by any sort of noise, or which is very clear, I will simply call it as a pure state. Okay, I'm not going to mathematics. In mathematics, it is known as the trace of the square of the density matrix. Okay, now why, and one more thing of pure state is that when you're having a block sphere, so you will be having a qubit, right? So qubit can be stored in a block sphere. So in a block sphere, if that quantum state is touching that sphere, so quantum state lives inside my block sphere, right? If the quantum state is touching that sphere, then I will call it as a pure state. If that quantum state is not touching the sphere but is residing inside my sphere, then I will call it as a mixed state. Okay. So what I will be doing here, I have my entangled bits, right? First, second stage, I will do something called as a purity measurement. Simply to put, I want to check the purity of that entangled gas. Okay. If I get to know that qubit 1, qubit 2, and qubit 3 are not pure in nature, then I will identify them and I will eradicate them. Got it as a simple tip. Okay, I'm not telling how exactly we are doing that, because we'll be having ancillary qubits and we'll be having swap gates, we'll be having that, this and all. I'm not going that. So I'm just telling you what is what. So we'll simply identify the states, and if that entangled states are not pure, we will simply take them off, because they are the guys who will cause the this entire downfall or something. And third deal is QAOA cascade mitigation. So what do you mean by this thing, Ante? What is a cascade in the first place? A domino effect. That's a simple thing I can say. So if one thing happens, then continuously one another thing will keep on happening. It's like a link. Okay, that domino effect. Because in dominos, if you just click the first guy, the entire thing will move, right? So the same thing. So the moment I observe these impure measurements, the next thing what I will be doing is to remove those impure measurements from my network. So because here you can see financial net, right? So the moment I observe impure measurements, I will try to remove those impure measurements from my network. So, and one more thing is I should be removing those impure measurements from my network in such a way that my relationship with of my financial network relationships are not broken. Okay, that's the main deal here. I should remove the impure guys, but my relationship should not break. For that, I'll be using QAOA. Because in QAOA, we have something called as a max cut problem. So in that max cut problem, we will try to partition my network. Okay, so that of a particular logic. Similarly, here also I will try to partition my financial network in such a way that I'll be removing these impure nodes as well as maintaining that financial network relationship. Okay, the financial relationship between the nodes. So for that, I'll be using this cascade mitigation. Okay, for that, I'll be using this QFF. So that is my systemic analysis. And how exactly it is adding advantage over classical? In classical, we need to check every combination. But here, because of this entanglement nature, we can simply swap them and see how they are behaving. So even after swapping, if they're behaving perfect, then they are pure. Why? Because if they are not pure, then if I swap them, they will be different. Obviously, they will act differently, right? So because of this entanglement nature of the quantum, I can simply check the purity by just swapping them and checking how they're behaving after swapping them. If after swapping them they behave the same, they're considered to be pure. But after swapping, if they are not behaving the same, they're considered to be impure. Simply do. Now, portfolio optimization. I already explained this thing to you guys in the beginning of the session itself. So here we can do it in two ways. One thing is by using the QAOA algorithm, and second thing is by using a variational quantum circuit. Okay, so that's the same thing here. And so these are the validations which we got after experimenting. So yeah, so yeah. So this guy, the blue color guy is a classical one, and this I don't know which color is this, but this color guy is the light color guy is the quantum one. Okay. So here you can see in everywhere the quantum one is having huge advantage over the classical stuff. So the test environment. So we tried to execute this particular operation by using 15 stock tokens, and after executing with 15 stock tokens, we got this particular thing. So the practical skill is obviously the hardware. So at this point of time, we are having limitations in hardware. So and the error rates as well, because the error correction codes should be even more perfect and stuff. And the circuit depth limitations and all these particular things which you can see in every quantum machine learning problem. So the same deal here. So hardware, error rates, the circuit depth limitations, and the problem embedding complexity. Because the data encoding is also kind of hard when we are dealing with this particular concept. So these are the practical considerations. And right now, we are able to do that with 15 to 20 assets. That is my stock tokens. And in the near term, we will try to move it to 50 to 100 assets. And at the long term, we can directly go to the real-time production. So yeah, this is an entire deal of this quantum risk management framework. So simply to put, we are trying to improve the entire risk management thingy with respect to finance by using certain quantum phenomenon which I explained till now. And recently we did with just 15 assets or 15 stock tokens because of the hardware limitations and everything. But in the near future and in the long term, we will try to definitely update it accordingly based on the features and stuff like that. And the benchmark is for O of n, we got O of root 10 thingy and over 150 times speed up compared to my classical analysis. So this is about the quantum risk management framework, which I wanted to explain to you. I think I utilized my 1 hour efficiently. So yes, so that will be it from my side. If you're having any sort of queries or anything, then yeah, you can ask me.
Thank you so much, Kian. Uh, Impressive. Learned a lot. I love how you kept connecting it to all of the financial options. You mentioned Monte Carlos, different max diagonalization, and a lot of the terms and things that we have been exploring. So they can kind of bring it together in a more um, holistic application. It is really great to see not only quantum in an applied way, but also a company and product that is being shipped out. So, a beautiful blend of academia and entrepreneurship. Thank you so much for your time and expertise. Because of where we are with the time, I think that if there is anything on the Discord channel, we can take a look at that. Otherwise, I think that we will. I don't see anything in the Zoom meet, and so we
Al Discord podemos echar un vistazo a
continue to
eso.
with some of the
Del
questions
contrario, creo
as they come up
que lo
in the
haremos
Discord channel because time zones, and
más
so they are
adelante.
definitely looking at the recordings and coming at us with additional questions. So if you don't mind, we might ask you to answer some at a later time.
Porque todos están en diferentes zonas horarias.
That said, thank you
Muchas
very much.
gracias.
And we are going to shift to our next presenter.
Vamos a cambiar a
And what I'm
nuestro
going to do
siguiente
is change
presentador.
the interpretation. I need to shift into the other one. And so, Danielle, I'm going to stop your interpretation. Nancy Reeves, are you, Nancy, are
I'm here.
you, yes. Okay, I cannot hear you, but I see her smiling. Okay. And then Allie, you're here, and let's just update this. Let me make sure that I can hear Nancy in English. Can you say hola, hola?
Hola, hola, hola.
Wonderful.
Hello, hello, hello. Bonjour.
Okay.
Hola, hola,
And
¿se
so,
escucha?
sí, 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 perfecto. Ahora sí se escucha. Vos estás en el audio original, and I'm going to share this very rapidly here. And then we have Daniel Ruiz bringing us the second part of variational quantum Einstein-solvers, and we are going to continue exploring quantum chemistry. This is the second part of a two-part series, and please take us away, Daniel. Thank you very much.
Vamos a comenzar con la sesión de Daniel, que es la
Gracias.
segunda parte de una
Bueno,
sesión.
nuevamente muchas gracias por el espacio, por la oportunidad de estar aquí con ustedes.
Muchísimas gracias por el espacio.
Continuaremos
Thank you so much for being
desarrollando lo
here
que
for
habíamos
the
explicado,
space.
pues los
And
fundamentos necesarios para entender un poco más el
today we're going
algoritmo
to continue talking about the
variacional
topics that we did in the
cuántico.
previous session.
Eh,
The basics needed to understand the
Así que
algorithm a little bit more.
vamos a hacer un
Quantum
breve
variation.
repaso por los temas anteriores.
So a small
Presentando
recap.
pues primeramente lo que hacemos en QNow. En
We're going
QNow
to
lo que
present what I
hacemos
do in
es
Q&A.
una generación y extracción y minería del conocimiento para
What we
ayudar a
do
las
is
empresas y
we are a
científicos
company that
a acelerar
generate
sus
and a mining
investigaciones, sus
company dedicated to
desarrollos
improve
para
understanding
nuevos
for
conocimientos.
enterprises and scientists, for
El
businesses and
equipo
scientists,
está conformado por Alejandro, que es el
accelerate
coordinador,
research, their
María
developments, and find new
Cristina,
patterns in data.
Hugo,
This is a team.
especialista en ciberseguridad, Mariano,
Alejandro, who is a
especialista en
specialist in
ingeniería de
chemistry,
software e ingeniería de sistemas.
Mariano,
Bien,
and this
¿de
is the
qué
team.
manera y para qué sirve y cómo usamos el
How
algoritmo
does VQE
variacional?
works and what it can solve.
Em, Habíamos visto en la primera parte
In the first
que
session, we saw what
este
was
algoritmo
VQE.
es un algoritmo
We
del
saw that the
más
algorithm, this
importante
algorithm,
y consta de
is
cuatro
one of the most
componentes.
important algorithms, and it
Este
consists
algoritmo, el objetivo es encontrar el valor más mínimo de
of four
energía. Recién
components.
acá
The goal is
lo
to
habíamos
find the
mencionado
lowest
en el tema
value
anterior, en la presentación
of
anterior.
the energy we had mentioned in
Consta de
previous
dos partes,
topics,
una parte
in the previous
cuántica y una parte
presentation,
clásica.
where it consists of two parts,
Y
a
sus
quantum
componentes van
part
a ser
and a
los
classical
siguientes:
part.
un operador,
Yes, and the components are
un
going to be as follows.
un estimador
They're
y un
going to
optimizador
be
clásico.
an operator, an answer,
Recordemos que cuando nos hacíamos
um,
referencia a un operador, hablamos de un hamiltoniano, ¿sí? Y un hamiltoniano, ¿qué es, ¿qué es un hamiltoniano? Es la
we spoke about a
descripción
Hamiltonian. We're going to talk about what a
interna de un
Hamiltonian
modelo
is.
matemático que describe las
This is an
propiedades de un
internal
sistema, ¿sí?
mathematical model that
Nosotros
describes the
para poder
properties of the
ejecutar
system.
o poder evaluar de manera directa un variational quantum eigensolver,
In
necesitamos
order
tener
to evaluate a variational
este primer
quantum
componente, ¿no?
solver,
Eh,
yeah, we need
Encontramos
first
que
to have
en
the
el
first
caso
component.
clásico es, o que de manera clásica lo que podemos hacer es encontrar en un
We found that in the
eigenvalue,
classical
el
case,
eigenvalue más mínimo o el con menor
within
valor,
the
¿sí?
eigenvalue or the smallest
Referenciado
value,
al valor mínimo de energía de un sistema, ¿sí?
or of reference to the minimum energy
Recordamos
value
que
of the
ya
system,
para
we will
cuando
remember
tenemos nuestro hamiltoniano, ¿sí?
that once we have
Términos
the Hamiltonian,
matemáticos, lo que tenemos que hacer es una especie de
what we have to do is
traducción
some sort of
a términos
translation
cuánticos o términos de compuertas que puedan ser
in quantum terms,
despejados pues por un hardware cuántico, ¿no? Para eso
or
utilizamos
that can be linked this to a
Estas son
quantum hardware, but not vice versa.
alianzas que ya existen y han
For
sido
that, we can use what is known as
nos deja
answers.
utilizar de manera predeterminada. Después, una vez que ya tenemos estas
Once we
componentes en
have
términos eh,
these elements
que puedan ser comprendidos por una computadora y que puedan ser
that can be
leídos,
understood by a
lo
computer,
que se va a usar es
what we
usualmente
use
ya una función clásica,
a
de
classical
algún
function
tipo de optimizador clásico, como puede ser un
with a
optimizador
type of
que se usa
optimizer,
bastante
classical
en el
optimizer,
clásico, o otro conocido de tipo Covila. ¿Sí?
or another
son
one known as COIDA.
optimizadores que
COIDA.
inclusive algunos de ellos se basan en el gradiente descendente de buscar siempre el valor mínimo de una función. ¿Sí? Esta es la parte
It is a
clásica
gradient,
de esta
the
función.
descending gradient, always look for the
Pero bueno,
minimum value of the
ya entrando
function.
aquí en la parte 2,
But now in the
con
second
el
part,
enfoque
quantum
ya un poco
chemistry,
más hacia la parte de química computacional
we will look into
y
the
computación cuántica,
computational chemistry part.
vamos a ver que
We're going to see
teniendo ya esos componentes, ¿no?
that having all
desde
those
un
components
hamiltoniano hasta la ejecución en, un- en una, en una
of a
computadora
Hamiltonian to an
cuántica,
execution
tenemos
of
que
a
tener en cuenta los siguientes
quantum
pasos.
computer, we have to take into
Primero
account
que
the
todo,
following
es
steps.
necesario
First of all, it's
preparar,
necessary
¿sí? Nuestro sistema
to prepare
desde
our
el enfoque
system
eh, químico hasta
from
llevar a la ejecución en un procesador cuántico. Para esto,
the chemical
pensemos en
system
una
to a
molécula
quantum processor.
que tenemos que definir en términos que sean
With this, we need
lo
to think
suficientes
about
para
a
poder
molecule that we can that we need to
ejecutando.
define in terms.
Si estamos buscando el valor mínimo de energía de esta molécula y demás en
We
una
were looking for the minimum
computadora
energy
cuántica,
value of
¿de qué
this
manera lo
molecule and so on.
representamos? Bueno, lo
In a
primero
quantum
es
computer,
definir
how do
qué
we
tipo de
represent
molécula
it?
es
Well, first thing
la que
is
estamos
to
abordando,
define what kind of molecule it is.
generar ya
If
lo que es
lucky, we'll be
un
addressing,
hamiltoniano, pero ya no un hamiltoniano
yes,
general,
already what
sino un hamiltoniano fermiónico.
it will be a
Mapear ese hamiltoniano
Hamiltonian, but
fermiónico
no longer
en
Hamiltonian
términos
general, rather a
de compuertas cuánticas para que pueda ser
fermionic
ejecutado.
Hamiltonian.
Pero ¿qué es un hamiltoniano fermiónico?
But what is a
Pues un
fermionic
hamiltoniano fermiónico
Hamiltonian?
es simplemente la descripción
It's
de un
simply the
sistema
description
no
of a
general,
system,
sino de un sistema que contiene partículas de este
but
tipo
not
de
general,
familia de partículas, ¿sí? En los
but it
cuales
contains particles of this type of
literal estamos
family.
contemplando incluso hasta los electrones de una molécula, ¿sí?
Particles,
Para poder hacer
which we're
esa
looking on a general
traducción
level, even
de
down
una
to the
molécula
electrons of a
a un
molecule,
hamiltoniano
in order
fermiónico
to do the translation from
versus
a
un
molecule
hamiltoniano
to a
cuántico.
non-fermionic
Ahí
Hamiltonian.
existen varias etapas y diferentes técnicas y modelos
And
matemáticos
a Hamiltonian and a
que
quantum one, and there are several
eh,
stages and different techniques
nos
in mathematical
menciona
models.
o se ven los ejemplos utilizando este tipo de técnicas de
Here we
llama
can see
Wingate.
some of the examples using
Utilizando
those
este tipo
techniques.
de modelos matemáticos podemos llegar a los términos necesarios para la ejecución
Through this, we
de
can go
este
to
hamiltoniano
to find the necessary terms for implementation
de las computadoras cuánticas, ¿sí?
within the quantum computers.
¿En qué se diferencia un hamiltoniano fermiónico a un hamiltoniano general? Bueno,
What
como
is different
mencioné
between
recién,
a fermionic
un hamiltoniano
Hamiltonian
fermiónico
and a regular
está expuesto en
Hamiltonian?
términos en el que contemplamos tanto la descripción y la iteración de los electrones justamente
The fermionic
en una red o en
is
ese
exposed in
sistema,
terms in which we contemplate so
respecto al
much
hamiltoniano
the
general,
interaction of
depende
electrons right in the
la
or in the
cantidad de
system
energía de un sistema, ¿sí?
and
Esa es la diferencia
respect
entonces.
to a general Hamiltonian, which only
El enfoque
describes
cuántico
the amount of energy in the
simplemente quiere
system. There's a
llegar
difference
de
between
definir
those two.
la
So
partícula
in the
como tal,
quantum approach,
la descripción de una partícula, de una molécula, a estos
we
términos.
always have to arrive the description of a
Bien,
particle as such.
vamos a ver ya acá puntualmente eh,
Here
cómo
we're going to
llegamos
go specifically,
desde una partícula, ¿sí?
how do we go from a
A
part
empezar a traducir esta partícula a términos de un hamiltoniano fermiónico, a términos de un
to
hamiltoniano
translate this
cuántico,
into a
para
Hamiltonian
encontrar ese valor
fermionic
mínimo de
or
energía.
to Hamiltonian?
Para esto veremos aquí justamente un ejemplo con
For
una
this, we're going to see an
partícula
example,
bastante básica que
very
es
basic.
el H2, pues
which is H2,
una molécula
which is a
diatómica quiere decir
diatomic
que es una
molecule.
molécula que es estable con
This one
otros
is a
átomos del mismo
stable
espectro
molecule.
de ese mismo elemento. Existen más partículas diatómicas, pero en este caso puntual estaremos haciendo
There are
uso pues
more
de esta molécula.
that
Em, ¿De qué manera
with
llegamos
two atoms of the same level, there are more
nosotros a
diatomic
traducir
particles,
una
but in this
molécula
particular case, we
en
will
términos
therefore only
computacionales,
make
¿no? En
use of the
términos
molecules
de
here.
software, inclusive en términos de código. Bueno, para ello nos ayudamos con
Molecule could be
librerías.
computational
Una de
terms
ellas
in software
que
terms,
pues
including in
estaba acá,
code
se me olvidó
terms.
mencionarla. PySCF.
I forgot to mention this
Cuando comparta los slides van a poder
when I share the slides.
investigarlo un poco mejor. Pero
PYSV,
prácticamente
you will be able
es
to
una
share
librería que nos
and
ayuda a
research it,
modelar justamente desde
but it's
las
practically a library
físicas
that helps
que
us
contabilizan
to model
cada átomo
um,
y nos ayudan a tener en
to,
cuenta
for the quantization of every single
diferentes
electron.
descripciones de esa molécula para que una máquina las pueda entender. Cuando hablamos de descripciones estamos hablando de características, ¿no? En este caso vemos que hay diferentes parámetros para describir una molécula,
There are
desde
different
una carga,
parameters. When we
desde
talk
unos
about description,
spins,
we're talking about
desde
characteristics. In this case,
inclusive
there are different parameters to describe a
la
molecule, from loading,
distancia
from
entre
spins,
cada átomo, ¿sí? Y demás detalles.
even the distance between each atom.
Posterior a esto de que ya tenemos nuestra molécula, ya la
Yes,
hemos
and
descrito,
after we
ya
have
la
our
hemos de
molecule,
una manera, digamos que modelado, ¿sí?
and once we've
Lo que
modeled,
haremos es generar
what we're going to
el
do is
hamiltoniano
generate
fermiónico, ¿sí? Que va a ser la base para posteriormente
the
pasarlo a
fermionic
términos de
Hamiltonian
compuertas cuánticas y ser
in order to
ejecutada
translate
tal
to
cual.
quantum gate terms.
Para esto también se usa la misma librería, ¿sí? Se
And they were
definen
running
también
quantum hardware on it.
diferentes parámetros
We're going to use the
del
same
número de
library.
electrones, de diferentes,
Different
digamos,
parameters
como
are also
inclusive hasta los
defined, starting with the
orbitales de
number of
cada electrón,
electrons,
¿sí? Y
including
demás
the
detalles.
orbitals of each electron.
Posteriormente, cuando ya tenemos bien mapeada y bien
Afterwards, once we
modelada
have it
nuestra
all well
molécula,
mapped,
¿sí? Lo que haremos es construir ya como tal el hamiltoniano,
what we're going to
basándonos de
do
manera
is going to build a
matemática, como lo hice
Hamiltonian,
al principio, el de Jordan Winker, para obtener ya nuestro hamiltoniano cuántico, ¿sí?
so we can have our quantum
Utilizando
Hamiltonian.
diferentes funciones que obviamente también están
That
dentro de esto,
obviously
¿sí?
are also inside the
Como resultado
key C.
y ejecutando pues todo este pipeline, por así decirlo, vamos a tener
The
ya
result of the
nuestro
execution,
hamiltoniano en términos
in a
por lo
way, this
menos
whole
de
pipeline
operaciones
will have our
matemáticas,
own
de
Hamiltonian
computación
now, not
de
just in
compuertas
terms of
cuánticas.
words, at least from
Una vez que
operations.
ya tenemos esos resultados,
Once we have
podemos
those
ver
results,
que se podría ejecutar directamente en un QPU
we can
real
execute it in a
y
QPU,
los resultados al final van a ser los siguientes.
and the results at the end will be as follows.
Es el mismo notebook que compartimos
It is exactly the same notebook that we shared last
la
time
anterior sesión.
in the previous session.
Un segundo.
Just a second.
Ok, ok. Déjame un momento. Esta es la manera. Un momento.
Just a second.
Bueno, no me estaría dejando ver el notebook bien,
I'm not
pero
able to see the notebook properly,
ahora veremos bien en detalle los resultados, ¿no?
but we will
Eh,
see the details
bueno,
closely.
genial. Otro detalle es para nosotros llegar a los términos de un hamiltoniano cuántico y de compuertas cuánticas, hay diferentes formas de llegar a esto, ¿sí? Una vez que ya
Another way
tenemos
to
nuestro
reach the quantum
hamiltoniano,
Hamiltonian and
como
quantum
todos los
gates,
pasos
there are
anteriores
different ways to
tenemos,
get this.
son los necesarios para llegar a la definición de un hamiltoniano, Posteriormente continuamos con el otro componente de este algoritmo, que es el ansatz, ¿no? De igual manera, Qiskit, como mencioné, tiene ya ansatz predeterminados, donde estos ansatz,
Daniel,
pues,
pausa un momento, por favor, porque creo que se le fue la luz a Nancy.
ok,
Um, Give me 1 second. Um,
ok, ok. Mientras tanto, yo voy buscando aquí
I'm
bien
going to I'm going to interpret into English, unless anyone else, Ali or someone else is willing to do it. I will do it. Just give me 1 second, Daniel.
of course.
So she was. Vos estás en español. We need to put it in English.
Do you want me to give it a shot? I can if oh, I might be speaking to the wrong language. Do you want me to give it a shot?
De español. Okay. Ali, can you give me a thumbs up? You can hear me in English. You're in the English channel, right? Okay. Okay, Daniel,
Yo te
let's do
escucho,
this.
yo te sigo escuchando.
¿Qué torta?
Oh,
Em,
I also hear you, but I don't think you can hear me.
can you hear me now?
I can still hear
Yo te
you.
escucho.
Daniel, you hear me? Daniel hears me too.
Yeah.
Okay. I'm gonna pause this.
Bien,
Go ahead, Daniel.
ok. Ok, ¿cierto? Bueno, resumamos de vuelta aquí un poco. Entonces,
We'll resume here.
antes que nada,
Just a moment.
para definir bien
Um,
nuestro
Before anything
Hamiltoniano,
else
que es
happens, we
nuestro
need to
componente de nuestro
define the
algoritmo,
Hamiltonian, which is the
es
first component,
definir nuestra molécula. Después de esa molécula,
to define our
definimos un
molecule
Hamiltoniano fermiónico, que
in a
básicamente es
fermionic Hamiltonian term.
modelar la molécula, inclusive
We need to model the
cada átomo
molecule,
y cada nivel de energía de la molécula.
the
Y
energy of the molecule,
adicionalmente a esa modelación, mapear ese Hamiltoniano
and we need to
fermiónico
map the
en un
Hamiltonian,
Hamiltoniano en términos
um,
cuánticos,
the
que es
fermionic Hamilton
básicamente
in quantum terms
la ejecución en una computadora cuántica
in order
real.
to execute it on a quantum
Em,
computer.
Bien, continuemos aquí. Entonces,
Good.
una vez
We'll
ya
continue here.
modelada nuestra, digamos que nuestra molécula, ¿sí? En
We'll
términos
model our molecule in
generales que nos permitan
general
hacer esta
terms
traducción.
that allow the translation.
Como resultado tendríamos el
As a
código,
result,
¿sí? Ya las compuertas o
we would have
los
the components,
componentes
the
necesarios
quantum
para hacer
components
ejecutados ya directamente en una
that are
computadora
necessary to
real.
execute on a quantum computer.
Vamos a ver directamente el código.
Let's go directly to the code.
Este código lo vamos a compartir con ustedes, pero básicamente eh, cuando hacemos la instalación de las librerías necesarias, tanto
We'll
las librerías
share
de computación
this
cuántica,
code with you
ejecutamos
directly,
este último bloque, que es el que tiene nuestra
and we're going
molécula
to execute the
Hamiltoniana.
code directly.
Vamos a ver que el resultado es el siguiente.
Let's see what the
Nos va a
result
dar,
is.
obviamente que un descriptor,
It'll give us a
un
descriptor
resultado
or a
un
result
cálculo de un modelo matemático
of a
necesario pues para
mathematical
generar
calculation necessary
nuestro propio ANSATS. Nos
to
va a dar
generate
nuestro
the correct
Hamiltoniano
ansatz.
y como resultado de eso, ¿qué vamos a tener? Em,
Oh, sorry, the screen problem was on my end.
ok, este no es. Vamos a tener
Thank
algo
you.
parecido como esto.
We're going to have something similar to what you see here on the screen.
Un Hamiltoniano
Printing the
de
Hamiltonian.
operadores de compuertas de Pauli y demás. Estos
um,
parámetros, como el
printing
Hamiltoniano
the
y la
polycomponents.
accuracy de Cholesky,
The
son
accuracy of
importantes
Cholesky
para el siguiente paso,
are
¿sí?
important
Siguiente
for
etapa que pues ya
the
sería la
following
construcción
steps
del ansatz como tal, ¿sí?
for the
Para la
ansatz
construcción del
as
ansatz
such.
mencionaba que
Ansatz
este
mentioned
sistema por
here
defecto ya
uh,
tiene
for
diferentes tipos de ansatz con diferentes tipos
there's different types of
de,
ansatz with different types of
digamos que de topologías en cuanto a circuitos,
topologies
¿sí? Tenemos
in different
el
circuits.
ansatz con entrelazamiento lineal, ¿sí?
With
Entonces,
the
de esta manera, el primero con el
linear
segundo,
orientation
y así sucesivamente.
successively from one qubit
Se
to the
define
next.
de esta manera, ¿sí? Con
So it's code
entrenamiento
in this
con
way with
lineal.
the linear
Y
component.
después también tenemos ansatz con
Next, we have
entrelazamiento circular,
ansatz with
¿sí?
the
El primero con el primero,
circular
después el primero con el segundo, y así
entanglement.
sucesivamente.
Then
Y
successively
se
with
representa de
the
esta manera,
next
¿sí? Nosotros podemos
qubits,
tener
and we represent it this way in the code
repeticiones
with one repetition
cercanas en nuestro circuito, de manera que
with
esto va a ser
at one
de
repetition in our
mayor
circuit.
impacto
This
tanto
will
en la profundidad de nuestro
impact
circuito
the
y en su
depth of
performance, ¿sí?
the circuit and the
Esto es un
performance.
detalle a tener en cuenta.
This is an important
Tenemos
detail to remember.
la forma de full entanglement, ¿sí? Que
So
son
the
los
form of full
componentes
entanglement
todos entrelazados con
is
todos
having
entre
all
sí.
of the qubits interrelated with
Bueno,
one another.
al final,
At the end,
teniendo ya nuestro ansatz claro
our
y nuestro
ansatz
Hamiltoniano en
are
términos
clear,
cuánticos,
and the
eh,
Hamiltonian is now in quantum
de
terminology
igual
or
manera nuestro
terms
estimado,
variables.
lo que tenemos que ejecutar como cuarto componente de este
We need
algoritmo
to execute
es
the fourth
el
component,
optimizador clásico.
and that's going to be
Esto
our
en el ejemplo
classical optimizer.
que posteriormente vamos a compartir, se utiliza el método
We're
Covila
going to use the
optimización
Kobila method
que está directamente en
that's
SciPy. Es
directly
una
already in the
metodología
SciPy.
muy conocida y bastante confiable.
Very reliable
Entonces,
and well
lo que
known.
hacemos es simplemente pasar los componentes
So what we
como
do is
parámetros
pass
a
the
esta
components as parameters into the Kobila
para
function
hacer clásica
in order to do the
digamos que
classic
el
optimization,
valor
and
mínimo
then we
nos va a dar como
obtain
resultado lo
the
siguiente.
minimum value
Ahora sí, vamos acá.
optimization,
Vamos a ver que
minimization.
este mismo Hamiltoniano
This
va a
same
ser el mismo
Hamiltonian is going to be
que empezaría acá
the same that we
en
start
nuestro notebook,
here
¿sí? Una
in
vez
the
que ya
notebook.
tenemos el Hamiltoniano,
And here we have the
nos
Hamiltonian.
vamos directamente
Then we go
a los
directly
ansatz.
to find the
Sea cualquier
ansatz.
tipo de ansatz, ya va a
You can
depender
use whichever type of
que sea el más
ansatz,
performante e incluso podemos crear
but you
nuestros
choose the one
propios
that will
ansatz
perform best.
y demás.
Additionally,
Bien. Y una vez que ya tenemos
and once we have
nuestro ansatz, ya tenemos
our ansatz,
nuestro, digamos que los componentes necesarios para
we'll say
ejecutar el
the
algoritmo,
necessary components to
lo
calculate the
que sigue nos
algorithm,
resta es ya ejecutarlo directamente
then we can
en
execute
el
it
notebook,
directly.
¿sí? Para esto, en el notebook que
So
compartimos, se puede
we
hacer
do this
directamente
in this section in the notebook that we've
de
shared
IBM Cloud, ¿sí?
in the
Nosotros
IBM
estamos
cloud,
utilizando un simulador.
and then
Como simulador vamos a
we're
ver que
utilizing a
los resultados
simulator.
son los siguientes.
Then the results are going to be the following.
Vemos que
We
cuando le
see
pasamos
that when we
los
pass the
componentes a nuestra función
components
o a
into our
nuestro optimizer
function,
clásico,
the classic
realizamos las
optimizer
iteraciones,
minimization function,
vamos a ver que cada iteración
we're going to
va a
see
arrojar
that
un
each
resultado
iteration
y
has its own
ya el
result.
que nos interesa
At the end,
de
the
toda la
result
ejecución de
of
todos los
interest to
movimientos
us from all of the
de este
executions of
algoritmo
all of the iterations
es
of the
el valor
VQE is
más mínimo
the
de
value,
toda la función.
the lowest minimum value.
Este valor, ¿por
This
qué es
value,
importante o al final nos quedamos solamente con
why
esto?
it's important
Porque posteriormente,
is because
continuando nuestro approach
as we
a
continue our
nivel de
approach
química computacional,
um,
lo
at a
vamos a
level of
aplicar
chemical
en diferentes
computation,
escenarios o en
we have
diferentes
different scenarios.
usos reales, ¿no?
different use cases or real situations
Podemos
where
usar,
we would
digamos,
need this.
este cálculo
For
de ground
example,
state o de
we
mínima
can use this to
molecularidad
calculate the
para
minimum ground
encontrar
state molecular
moléculas
energy state
estables
in order to
si
find
tuviesen parte
what would be a
del
stable state.
paso de lo que conlleva
So
realmente
this would be
un
a
descubrimiento de fármacos
phase
o
or
un
step
descubrimiento de nuevos
uh,
materiales.
to
Esa es la
discover
parte
in
de todo
materials or
este
chemistry.
rompecabezas, ¿sí? Definiéndolo pues de diferentes moléculas, ¿sí?
So this would give us an end
Y
result
lo
of
que nos va
different
a limitar acá
molecules
es el
that would
tamaño
be
de la
stable.
molécula, ¿sí?
So in this molecular
En nuestro átomo
form,
hamiltoniano de una molécula de dos átomos con dos electrones,
we would use the
esta
Hamiltonian
cambia en
for
proteína inclusive, va a
two
cambiar de forma.
molecules
Eh,
for a protein to find
Otra,
a different
otro
result.
caso de uso que podemos ver
A different use
a
case that we
este
could
algoritmo
see
es para
for
encontrar
this algorithm is to find
bioactividades en
bioactive
proteínas con receptores
proteins
específicos, ¿sí? O con
with
targets específicos.
specific
Y para el
targets.
descubrimiento de materiales también,
And for materials discovery,
utilizando diferentes
utilizing different um,
capacidades y
capacities
descripciones
or
de
descriptions
moléculas que nos
of
permiten
molecules
saber
that we
cuál
want to know
material es
about
más estable
to find out which material would be the most
relacionado
stable
a algún tipo de reacción
related
o
to a type of
materiales.
reaction.
Es que ahí Alicia es más
Uh,
experta que nosotros.
and that
Digamos,
potentially those with a material background might be able to offer more
para
insight.
tener un panorama general,
Um,
¿para qué nos sirve
this would
esto?
offer a
Se
general
podría decir que para
view panorama into
específicamente dentro del lab,
these kinds of
lo que
discoveries.
tratamos de hacer con este tipo de
What we try to
algoritmos
do with this type of algorithm
justamente en el desarrollo
is
de nuevos fármacos
to
es que
contribute to materials
estemos
drug discovery.
viendo
So, for
diferentes
example, target
etapas,
identification
¿sí?
uh,
Desde
and
inclusive
the different
eh,
steps,
de las etapas
including
de
the
identificar un target
steps for
hasta
identifying a target
la prueba
and
con,
doing
digamos,
the
in vitro
preclinical
o
testing. So,
con células vivas, ¿sí?
when you're thinking
Todo esto
about living
lleva a
cells,
que estas pruebas o que este
these
proceso
different trials and
de
steps in the
diseño
process for
sea infinitamente
drug discovery and
computacional, o sea, in silico,
design
¿sí? De
have
modo
in
que podamos, por
silico
ejemplo,
options
probar un
for
fármaco
how to
en humanos
carry out
o en
the
personas
various
que se
steps.
trate de modelar directamente
So we're
en una
trying
máquina.
to directly do this in the
Que
computer.
pues podría llegar a ahorrar tiempo, podría
So
ahorrar
it's
inclusive
a way
hasta
that you
vidas
can save time and
para
save
simplemente
money
descubrir un
um,
fármaco.
in the process
Eh,
of drug
en
discovery.
general, en ese tipo de
In
pipelines o
general,
enfoques, se
with this
empieza
type of
con
focus, you
muchos
start with
candidatos
a
y esos
lot of
candidatos
possible candidates.
se van filtrando
And then
hasta
you
que
start
llegan
filtering it
a los
down
mejores
to
y
the
al
ones
final de
that
todas esas
seem
universo
the best through that
va a
process.
quedar un
And
candidato
then
que
once
sea
you've gone through that filtering process, you
internacionalmente
get
validado,
one candidate, one
esté en
compound.
Europa, si es Estados Unidos, que cumpla inclusive la
Um,
explicabilidad de los algoritmos
in the United
de cómo se
States,
llegó a este
this
resultado
has
y que cumpla diferentes
shown
regulaciones como la
certain
normativa
specific steps that you have to take in
para
order to get through to get that one
pues
compound that's approved,
eh,
including testing in humans and in
distribuir el
animals.
mensaje pues de que
Um,
los algoritmos que tenemos hoy en día los podemos
so
usar
thinking about the algorithms that we have available to us today, we can use it in different scenarios.
el hardware
Um,
y bueno,
and
empezamos
this is going to
a
be
crear
partially
cosas.
tailored to the hardware that we have.
Gracias.
Um, thank you.
Si tienen alguna pregunta, la
If you
podemos
have any
responder
questions,
directamente en el Discord.
you can put it in the Discord directly or in the chat here.
Thank you, Danielle. That was incredibly comprehensive.
Gracias.
Déjame ver si hay algo en el Discord. And doo, doo, doo. Oh, there is. Okay. No, these are other questions. Okay, so we will be answering any questions in the live questions section for anyone who has questions during the recording as well. And let me just share my, oh, I think did a lot of things with my language here. So where am I in my language? I'm still in English. Okay, wonderful. Okay, so I'm going to just do a quick share over here to introduce and so for the last time in this series, we are going to have our one and only Sudikan close us, close the quantum machine learning journey with QVCs and QNNs. And we are going to shift our translation again. Ali, thank you very much. No doubt you did amazing.
Thank you. It is harder than it looks.
So hard. So hard. After a while, you're like, oh, don't try to understand, just say it. So they can. I think you
Yes,
need
am
to
I
unmute.
audible?
There you go.
Am I audible?
Yes.
Okay. Yeah. Good day, all of you. So today is the last part, and as we all know that today a very small portion is left, the final part of application of all those things that we have learned into QVC or QNN. So we'll get into it. But before starting this talk today, I would like to say that this talk will be a very small time talk because it doesn't require much time to do this portion. So it's mostly code based. So we'll go into the code as soon as possible. But after completing it, I would love to show something, and I hope all of you will love that. So yeah, not only today's class is important, but what I'll show after that is also very important because I have been waiting for it for a long time. So that's a surprise, I won't say. You keep guessing. You find it after 10-15 minutes. Okay. Okay. So yeah, is my screen visible? Can you please tell me, is my screen visible? I
It is
hope
not.
not.
Mm-mm.
Yeah, okay, okay. So let me see. Uh okay, just screen to screen one. Okay. Yeah, is it visible now? Is it visible now?
Yes.
Yes.
Oh, okay, 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 okay. Okay, so yeah, so today is the last part, and which is QVC or QNN. So all that we have learned till now, from data encoding to what is classical machine learning to what is quantum kernels, how to use that. And after having learned all things, this is the end thing. And in this thing, there is nothing much theoretical. It's mostly how you apply all those things and just put up a circuit so that you could get the result out of your data. So it's a very short lecture, but this is what it is. Okay, so first, because before that we need to know what is QVC and what is QNN. So first thing is, what is QVC and what is QNN. So what is just 1 second. Yeah, okay. So what is QVC? So QVC is any quantum circuit by which you want to get a value on an observable. It's as simple as that. A quantum circuit by which you want to get a value, a simply one value on an observable. So suppose O is your observable. Is my pointer visible here? Can you see my mouse? Okay. So
Yes.
if O is my observable, you have any function that you define by psi theta. You get a part of that observable on O. Simply, that is your QVC. Now you can apply a cost function to it. So here C theta is your cost function. When you apply a cost function, you just train your data in such a way that you keep on getting some good values. Okay, I'll show you a code working also. Just hold for some time. So I'll show you two codes today. One for a real application on an image representation, another one on how this could be used in another set of classification problem. So this is your QVC. So any circuit with an observable is your QVC. Finished. Now, so why is it called variational? Because in QVC you can have parameters which you can vary. So see, we know there are two kinds of parameters. One set of parameters that we cannot change, another set of parameters that we want to change. So a circuit which has parameters that could be varied, that could be approximated according to the system state is a variational parameter circuit, and VQC uses that kind of variational things, hence it is VQC. Okay, so in VQC, the simple steps will be to load our data, to create a trainable function, having some weights and measures, and then to get a measurable output out of that. That is simply VQC. Okay, now a QVC. Now, what are the different types of QVC? So we have VQE, QAOA, VQC, QNN, and there are many other subparts of it. So we won't go in that depth, but we will restrict ourselves to these four portions. We are mainly interested in QNN. So I'll just give a quick intro to this thing. So VQ is for finding out the energy state or energy Hamiltonian. So it is popularly known as variational quantum eigensolver. So see, the H here represents the Hamiltonian of a system. Hamiltonian is an operator that is used to calculate the energy. So VQE is a kind of QVC that we use for finding energy. Now, QAOA is another set of VQC algorithm, QVC algorithm, which is used to find roots or used to find the best combinations possible. Suppose you have 3-4 points and you want to cover all of those. So how will you create a network between them so that you can finish it in a faster and more efficient way is determined by algorithms like QAOA. Next, you have variational quantum classifier. So that is VQC. So VQCs are also used. It's similar to neural network. It's similar to quantum NN, but the only problem here is it uses only trainable variation layers, and it does not resemble exactly a neural network kind of architecture. So VQC and QNN are almost similar with a simple minor difference between them. And at last we have our QNN. So QNN represents a neural network, exactly a neural network. And how a neural network would behave is similarly how a QNN would behave. But other things will be same. So you have a embedding, you have another function, you have a observable, and you have a cost function, a classical cost function by which you optimize your circuit. And as I told you today, mostly our work will be on the basis of code demonstration. So we need to go for the four parts of it. So for the four parts of Qiskit pattern, first one is mapping the problem to a quantum circuit, optimizing for the quantum execution, executing on Qiskit primitives, and post-processing to return the classical data format. Okay, so now we'll go for the code understanding. Just bear with me. Just bear with me. Can I stop the share? Can I pause the sharing? Is my sharing paused?
We currently see your desktop and your pointer is not moving, so probably paused.
We see your desktop and your pointer is not moving.
Okay. Great. Just 1 second. It's almost done. Let me load the codes. Just 1 second. Okay. Okay. Just 1 second. Another part has to be loaded. Okay. Yeah, almost there. Okay, now can you see my screen? Is my screen visible now? Okay, so let's look at it in this way. So we have a quantum image. Now, why we are saying a quantum image? So suppose we created a checkerboard kind of image, and suppose we created a circuit. When we are saying quantum image, that means we are encoding each value pixels of the image to the encoding part of the circuit. So this part at the front, this is my encoding part. Is that clear? Now, suppose I'm initializing the parameters as 0. So keep one thing in mind, that these are my hyperparameters. Hyperparameters mean those that we won't be changing, those which are fixed. So image values are there. Hyperparameter means the image values converted to the angle values. So we are using angle encoding here. Converted to the angle values won't change. So they are hyperparameters. Next, we have parameters. That means we want these values to change, and we have initialized them. That is, every weight that you want to put has to be given some initial values, and for all the angle values we have put here 0. Now, as I said, for any variational circuit, second thing you need is an observable. Over that observable, you find out a expectation. So we define these Pauli observables such that Z on the first qubit and I on rest other qubits. It mean that I want to find out the Z value corresponding to the qubit 1. Now Z value can be 0 and 1. So what do I want to find out? I want to find out how much my Z value or the first qubit value is closer to 0 or 1. Similarly, a Z in the second part represents Z value on the second qubit. So how much the second qubit behaves towards K0 or K1. Similarly for the third, for the fourth, for the fifth, and for the ninth. Now we defined the observable. So we had the encoding, we had the trainable circuit, we defined the observable. So three main parts of a QVC algorithm is done here, right? Okay. Now we create an estimator. So here we use air simulator on 10,000 shots. So we use this estimator where we used air simulator to do the estimation of it running in its backend. Then we calculate the L1 loss. L1 loss is just some subtraction of the true value from the predicted value. So we put a L1 loss, and L1 loss is a classical loss. So it's not a quantum loss. So we measure the outputs, we get some values, we compare it with the target image. Again, we put that into the trainable circuit, and the trainable circuit modifies itself similar to a neural network. So what it does is it trains itself and updates its parameters automatically. So this is our training loss, and this is the final reconstruction image, and this is how the image would finally look and how the image was shown when it just started. Okay, so this was one part of it. I'll go to the code demonstration of it very fast. So this is the code demonstration of it. Can you see the code? Is it visible? Is the code visible? Can anyone please confirm? Is the code visible? Hello, is the code
Yes,
visible?
yes.
Yes,
Visual.
it's visible.
Okay.
Continue.
Thanks. Okay. So what we are doing is we are doing this, the thing that I showed you just now in the PPT. We are just doing it on the code. So first we are loading the Qiskit libraries, and we are creating an image of our own. So we created this image. Now to put it into the circuit, first we need to have the linear value. So we flatten the image. After flattening the image, so see, we have the values 0, 1, 0, 1, 0, 1, 0, 0.750. So see, 0, 1, 0, 1, 0, 1, 0, 0.750. Now we normalize the flattened image. So we see that as the minimum and maximum value was 0 and 1, so it retains the original value only. We created an encoding circuit and a parameterized quantum circuit. So see, RY, this portion creates the encoding part. It's an angle encoding. And this portion creates the variational circuit part. So this portion will be trained. This portion will be used for the hyperparameter, that is for the non-training part. Now, after that, we visualize our circuit. You just saw this circuit I showed you in the slide a little bit ago. Okay, and we will be creating the Pauli observables over which we want to view the our final outcome. So see, these are the Pauli observables. I also showed this to you. Now, so this is the reconstructed image state vector. So we are declaring the state vector, getting the state vectors from its instruction set. Then we are putting the expected values here and we are reconstructing the image. So from the estimator, we are running through the circuit and see estimator.run times length of observables, comma observables. So we are getting the observables, storing the value of the observables inside the from the state vector inside the result, and we are reconstructing with the expected values. Okay, now see, we defined here the air simulator, use the air simulator in the backend, and number of shots we defined as something 10,000, and then yeah, with 10,000 shot 1 lakh shots, sorry, and then we declare a L1 loss. L1 loss, I said that is just the value minus the target. So what expected value we got minus what was the original value of the target. We calculated the L1 loss, and now so this was all defined. So we will put this into the actual working of the circuit. So we define the initialization of our parameters, that is which we will try to train. Then we will find, and this is the target image values, and then we'll just put it in the circuit, use Kobila, and then we'll train it. So on training with L1 loss, we find out that its loss gradually decreases, and finally we will be getting this reconstructed image as the final result. So this was the code implementation of the slide that I just showed it to you. Okay, so this was on the simple implementation of an image reconstruction using a QVC algorithm. Okay, now I will also take you through the QNN part of it, and I will show the beauty of QNN and why it is so important to use some kinds of entanglements so that you could find the relationship between the data. So I'll take you fast forward through it. So we created some data. So what was that data? These are some images. Now, if you look carefully, there are some horizontal yellow lines and there are some vertical yellow lines and some horizontal yellow. There are many other images also. I'm just showing here 8 images. So we give them some labels. We create a VQC circuit. So first part of the VQC circuit will be for the embedding. So we create a Z feature map embedding here. This is the answers. What will the answers do? So we told that we need a parameterized circuit. That parameterized circuit will have its value updated as per the loss, right? So this is that parameterized circuit, and generally we call the parameterized circuit as ansage. So this is the ansage, and we will create a C0 list. So this C0 list is nothing but the entanglement pairs that we want to take custom. So what pairs are we taking? Between 0 and 1, 1 and 2, and 2 and 3. So if we see the circuit, so this is our entire circuit, but we have taken entanglement only between first two 0, 1, 2, and 3. So what is 0, 1, 2, 3? Let me tell it to you again. So if you look at this image, that is 0, 1, 2, 3, 4, 5, 6, 7. So if I am creating a link between 0 and 2, 3, that means I'm only linking 0, 1, 2, 3. That is only the top row. Anyways, so then we try to run this circuit, and this is our final circuit that has been done by decomposition into the quantum hardware that we want to use. So we decompose that, we put a measurement, and then we run it, use the loss function here. So here we also use the mean square error loss. We train the circuit and use the optimizer. We ran it at IBM Torino, and after passing through the pass manager, we executed it using Qiskit primitives, and we find out that at the end of it, the loss that we will get has reduced, but the training accuracy is only 60%. Now, why 60%? So is 60% bad? Maybe 60% is a good accuracy for this thing, but we will observe a special kind of thing. If we improve that, we will see how this accuracy could be improved. Let us look into it. So we get accuracy around 60%, and we check our loss. We see that, okay, our loss is decreasing, but it has not decreased much. It has decreased up to 0.9 from 1. So that's not a big decrease in loss. Now, let us see how many images were not identified correctly. We found out 24 images were not identified correctly. If we look at the 24 images, can you observe a pattern here? The pattern is, see, this is in the second row, vertical, second row, vertical, second row, vertical, vertical, second row, vertical, vertical, second row, vertical. So whatever I'm saying, all of my words are going into two terms. One is vertical, one is second row. Now, if we observe carefully, we see that the vertical images are not identified. The second row is not identified. And if we look back into what we had done before, we can see that previously in our circuit, we have only entangled the first row and not the second row. So this is a very important thing. If we would have entangled the all rows, then the 24 misclassified images could be something different, but we find a pattern in the misclassified images where we see that specifically all errors are present based on the last 4 qubits. That is the second row. And if you see about vertical, it comprises of both the first and second row. So anywhere there is second row, there is an error prevalent. So what we did then, we created another entanglement set where we took all the possible rows one after the other. So see, we entangled all the possible rows. So from first, second, third qubit, that is for the first row, and fourth, fifth, sixth qubit, that is the second row. And we see that after doing that and continuing all the processes, we see that the loss has decreased from 1 to 0.8. So previously it was from 1 to 0.9. Now it is from 1 to 0.8. So we see that the loss has decreased further only because we put more entanglement into the second level also, that is second row also. And after all the training, we find out that the accuracy has increased to 80%. So I would conclude there is more work into it that is not required, but in this part, I will conclude this thing that why I showed this code work is because if you design a QNN circuit, it's not about getting just a result, it's identifying the relationship in your input data which you have to identify properly so that you could actually use this circuit to find out something important. So what would you have done if this was a classical program? So if it would have been a classical program, it would have been dependent on data. So more number of data you have, the better outcome you will get. But in quantum, it's not about data, it's about how you design your circuit based on your input data. So if your input data is such that it has relationships between first and the last qubit, you should design your circuit in a way so that you could create a relationship between your first and the last qubit so that that relationship could be identified properly. So the main point from today's class is that we should create our circuit intelligently so that it is able to identify the patterns in our data, and the type of data that we use will have that relationships inherent in between them. So yeah, that's all for today. Thanks to all of you, and the QML class closes here. Thank you.
Please, a round of applause for Sudikin. I have learned so much in this journey with you, Sudikin. Things I thought I understood that I understood completely different, and I think that everyone is always looking for more time with you given your depth of knowledge in physics and quantum machine learning, geospatial, everything. We are so lucky to have you presenting. So thank you so much for culminating this quantum machine learning course. We heard from our speaker Gian on some financials. You heard from Daniel Ruiz today on the critical algorithms that you can also use, like BQE. You saw real world applications, products, people making money on this. It's incredible. There's so much you could do. Material science, Danielle, actually, I think this also concludes the VQE portion, right, for quantum chemistry?
Huh,
Yeah.
I
So let's
think
give
so.
also Danielle Ruiz from Q Now a round of applause for all of the expertise and time and dedication. This is a labor of love, I tell you all. We are volunteers. We have lives and children's and families, and it is out of passion for science and all of this that we bring these programs to you. So please make good use of the Discord, ask questions. It dawns on me that until you take the test, you may not realize the questions you have. So hopefully, by this weekend, when you take the fundamentals quiz and then you attempt to go for the badges, that you take advantage while we have support in our Discord channel to ask the questions that you can. We are going to dive deeply into cryptography for next week and some of KQD and PQC, kind of showing you some roadmaps. We're going to launch the rest of the hackathons today. We'll put one out there so you can get started, have time to um, let it kind of sink in. And for those of you who had previously participated in this humanitarian challenge, I really invite you to take some time to take a walk, put your feet on the ground, think about the things that you really would like to make better in the world that we live in, and know that we have some amazing prizes for you. So more to come on that. And stay tuned for the recordings. I'm putting the interim recordings with Zoom over there. Just select your language, and we were having some issues with the compilation of some of the language files. So just bear with me for the YouTube, but further than that, you'll get it real time. As soon as this comes up, I will put it there so you can watch it. Wonderful.
Ma'am,
Yep. Go ahead.
I have something to show.
Oh boy.
Sorry, where is that?
Oh, yay!
And
The hooks?
can you okay? I don't know whether it can be seen or not. It is not taking properly. Okay, anyways.
Oh, wonderful. You have to
Cool.
open it. You have to open it. The grand reveal.
Yes, yes, please.
Okay, let me. Can I, my background is not that good, so let me remove it. Just 1
Oh,
second.
don't worry. You don't have to. Yeah, you can. You don't
Yeah.
have